Hi guys! Today we're going to start Chapter 6. And Chapter 6 is a completely different set of information than what we've just finished in Chapter 5. You'll recall in Chapter 5 we were working with discrete probability distributions, which have variables that are countable. In this case, we're working with what's called the normal distribution, and you're going to see a graph that we've talked about before come back into the limelight. A lot of this chapter deals with the use of a specific table, a couple of them actually, and a lot of word problems, which make this chapter a lot of fun. I know, you don't think word problems are fun, but I do. So that's the way it is. My advice for you whenever you start this chapter is to go to your book in section 6.1 and read through the introduction. I say that because the book does a really good job, in nice layman's kind of terms, it does a good job of describing what this chapter is going to be about. Like I said, it'll just give you a good foundation to do that. So my advice would be to pause this video and go read that and then come back to it. So you have something to connect this to so that it's not just a bunch of random information that's being thrown at you. All right, so assuming you've read that then, we know that this particular chapter is about what's called the normal distribution. And you may or may not recall that earlier in the year we talked about 3 types of distributions in general. We talked about the right-tailed distribution, and you'll recall that it was named that because the tail of it was on the right side. We also called that one positively skewed, if you'll recall that. Then we had the left-tailed, or negatively skewed, with the tail on the left side, majority of the values on the right side. And then the last one we had, and this is the one that we're going to focus on in this chapter, was that nice bell-shaped distribution, or that symmetric distribution, if you want to think of it that way. And it's called symmetric because it has a line of symmetry straight down the center. You may also recall that that particular distribution, the mean, the median, the mode, were all equal, or approximately equal, and right at the center of the distribution. And that's going to be of utmost importance as to what we're doing in this chapter. So, section 6.2 is the introduction. Whoops, I'm off the page. There we go. Let's try that again. Section 6.2 is the introduction of the normal distribution. All right, the normal distribution. The normal distribution has this general shape, as we've already talked about. It's got its mean, its median, and its mode at the center. It does work or operate from an equation that you could graph. This equation is kind of massive. It's going to feel very confusing to look at. We'll kind of talk about it a little bit, but keep in mind that you're not going to have to use the equation directly. A lot of what we are going to be doing will deal with tables of values that have already been created, and we won't have to come back to this much. But you do need to understand the equation so that you can understand how it gets used. So in terms of what this equation looks like, y equals 1 over sigma times the square root of 2 pi. Not too bad so far, right? That sigma, do you remember what that is? Population, standard deviation. So that one's a variable we've already seen before. That gets multiplied by e to the, and this is kind of a funny looking exponent, it's a fraction, negative quantity x minus mu squared over 2 sigma squared. Big, right? All right, so in terms of what that means, mu, as you may or may not recall, is your population mean. The average of all the values in the population. Now, your book, if I recall correctly, in the introduction, talks about heights as a continuous variable. If we're talking about heights of adult, let's say adult males in the U.S., it is physically impossible or nearly physically impossible to collect all of their heights. So this, we're not going to see as a numerical value. We're talking in theory. All right, next we have the population standard deviation, and that's our sigma. I'm going to abbreviate here. The population standard deviation. Those two values can change. depending on what your variable of study is, the mean of that population and the standard deviation of that population would be different than, say, another normally distributed variable. For example, if we compare the heights of females of a certain age to the heights of males of a certain age, I would expect that the mean for males and the mean for females would not be the same. Likewise, I wouldn't expect their standard deviations to be the same. So that kind of poses a bit of a problem, not in terms of the function, but in terms of solving word problems related to this particular function. So with that in mind, we need to kind of have a way to discuss distributions that doesn't rely on this. In terms of what's going to happen with this curve, this is actually a family of curves, which I know probably doesn't mean much to you at this point because we haven't talked a lot about functions in this class. But what that means is this curve could have the shape as I drew it there, or it could be a curve that is much steeper than the one I originally drew, or maybe it's one that's more shallow than the one I already drew, that's closer to this kind of shape. And those heights, more or less, the difference in the height here, is due to the values of sigma and mu. That's where we end up with a dilemma when we start to try to use this function to solve problems. So instead, we do what's called normalizing it. We're going to talk about that in a minute. So let's talk about some of the properties of this distribution and what would be true of any of those family of curves. Doesn't matter which one I use. Properties. And there are several. First one, it should be bell-shaped. In other words, they all have the same general shape, which we've already discussed. Shouldn't be anything new. 2, the mean equals the median, which equals the mode, and all three are located at the center of the distribution. And that we've already talked about as well when we did distribution shapes, so that shouldn't be new. 3, it is unimodal. You'll recall that modes are where the graph has its highest point. It's the value of x that corresponds to the largest value of y, or your largest frequency. Unimodal just means that this one is going to have one single high point. It's not going to have 2 or 3. Won't be uniform, or they're all the same height. It's got to have some mode. 4, the curve is symmetric about the mean. Now, what in the world does that mean? Okay, so let's talk about the distribution shape just a bit more. We know that it's bell-shaped. My bells get funnier and funnier looking all the time, so I'm not judging you on your math ability. Don't judge me on my math ability. That's not what I meant to say. I'm totally judging you on your math ability. Don't judge me on my art ability. Yeah, you know what I meant. All right, so here's our mean at the center. The fact that it's symmetric about the mean just means that one half of the graph is a reflection of the other across that line. Think of it like a line of symmetry in geometry when we talked about that. So here, one half of the graph will lay to the left of the mean, and one half of the graph lays on the right side of the mean, which is why the median is there as well. And that's just what the word symmetric means. One half is a reflection of the other half. All right, our 5th property, the curve is continuous. There are no gaps, there are no holes. The curve is continuous. Nothing too shocking there, right? 6. The curve never touches the x-axis. You'll notice as we draw these that I'm always drawing them with this straight line along the bottom edge. That line here along the bottom, that is your x-axis. Notice also that the y-axis is not there, and that's due to the fact that when we change the values of sigma and mu, it can shift the graph to the left or right, and the placement of the y-axis really doesn't matter because we're never really concerned with how tall the graph is at a certain point, so that doesn't matter in the context of what we're going to be doing with it, so we just leave the y-axis off. That's not a convention that I've just made up. It's a common convention to leave that y-axis off. But that straight horizontal line that we're drawing underneath, that is the x-axis. All right, 7. The total area under the curve is 1. Meaning, if I were to kind of chop this apart into smaller sections and find the area of each one and add them together, the area should be 1. Now, trying to cut that apart into smaller sections and finding the areas of those sections gets to be a little difficult, and that's where some calculus comes into play. Basically, what they end up doing is we end up taking this curve and dividing it up into a bunch of little bitty rectangles, finding the height of the rectangle, multiplying it by whatever the width of the bar is, and we like these bars to have the same width, and then we add those together. Now we can see that that's going to be an approximation because these bars, and the way I've drawn them, are slightly greater than or above the actual area that I need. Likewise, if I draw them the other way, I can draw it so that it's below, like so, where it's less than what it should be. And so that poses a little bit of a problem there. But in Calc, you'd learn how to find the area of under curves between that and the x-axis. And that's what has been done here. So in this case, the total area under the curve is 1. And that's going to be really important because with probability distributions, you'll recall they have to total 1. Which means this 1 is going to be thought of, and all the areas under the curve will be thought of as probabilities, a little later in this section and in section 3. Okay, so the other thing that we need to look at, and this is totally review, is what we knew as the empirical rule. The empirical rule, as you may or may not recall, dictates what percentage of the data values should be within 1, 2, or 3 standard deviations of the mean when the distribution is bell-shaped. So our bell-shaped distribution in this case, let's look at 1 standard deviation above or below the mean. So our mean's in the middle. And I'm going to go 1 standard deviation below the mean and 1 standard deviation above the mean. And whatever that value of the standard deviation is, that will determine that distance between the mean and that bar. Now the empirical rule says that in this area, between those two, should contain 68% of the data values. And that 68% is actually the area under the curve between those two values. So it's not just a value that comes out of nowhere. We also know that if we go to 2 standard deviations to the left and right of the mean, there's a specific percentage that applies. So here again, we've got our mean in the middle. Now we're going to go out a little further at 2 standard deviations below and 2 standard deviations above. And the empirical rule tells us that this particular area or portion of the graph should contain 95% of the data values in the set. So there again, that 95%, 0.95, is the area of that shaded region. And lastly, if we go out to 3 standard deviations above and below the mean, that area has to encompass an even larger portion of our data values, specifically 99.7%, which tells us that area as well. All right.